Imagine standing on the rust-colored surface of an alien world, looking up at a sky that has turned from butterscotch pink to azure blue. You take off your helmet and breathe deeply, filling your lungs with air that, just decades before, would have killed you in seconds. Around you, green shoots push through the Martian soil for the first time in billions of years. This isn't science fiction. This is the audacious dream of terraforming Mars, and some of the brightest minds on Earth believe it's not a question of if, but when. But here's what should make your heart race with equal parts wonder and terror. Transforming Mars into a second Earth would be the largest engineering project ever attempted by humanity, dwarfing the pyramids, the Great Wall, even the entire Industrial Revolution combined. We're talking about reshaping an entire planet, manipulating an atmosphere, warming a frozen world, and essentially playing God with a celestial body that has remained unchanged for 4 billion years. The question isn't just whether we can do it. The question is whether we should, what it will cost, and what we might lose or gain in the process. Close your eyes for a moment and ask yourself this. If you could press a button right now that would start the terraforming process, knowing it would take generations to complete and that you'd never see the final result, would you press it? Would you commit humanity to a project that might consume the resources and efforts of countless generations, all for a world you'll never walk upon freely? Hold that question in your mind as we journey through what might be humanity's greatest adventure. Mars hangs in our night sky like a bloodshot eye, watching us with ancient patience. The Romans named it after their god of war, and when you understand what it would take to conquer this world, you begin to see why. Mars is not welcoming. It is not forgiving. With an average temperature of -80 degrees Fahrenheit, an atmosphere so thin it's practically vacuum, and radiation levels that would give an unprotected human radiation poisoning in hours, Mars is fundamentally hostile to life as we know it. Yet this rusty desert world is the most Earth-like planet we know of in our cosmic neighborhood. It has water ice at its poles and buried beneath its surface. It has a day that's remarkably similar to Earth's, just 37 minutes longer. It has seasons, canyons deeper than any on Earth, and the largest volcano in the solar system. And here's the fascinating part that most people don't realize. Mars wasn't always the frozen wasteland it is today. Evidence suggests that billions of years ago, Mars was warm, wet, and possibly even hospitable to life. Rivers carved channels through its surface. Lakes dotted its lowlands. An atmosphere thick enough to support liquid water wrapped around the planet like a protective blanket. Something catastrophic happened to Mars. Its magnetic field died. Without that invisible shield, the solar wind stripped away most of its atmosphere over millions of years, like pages torn from a book by an invisible hand. The water evaporated or froze into the ground. The planet essentially died, leaving behind a desiccated corpse of a world. But here's where the story gets interesting. If Mars was once capable of supporting liquid water and a thicker atmosphere, could we bring it back? Could we resurrect a dead planet? The concept of terraforming was first seriously explored by science fiction writers and then picked up by scientists who dared to ask, what if? The word itself comes from the Latin terra, meaning earth, and forming, meaning to shape. We would literally be earth-shaping another world. The renowned astronomer Carl Sagan was one of the first mainstream scientists to discuss the possibility in the 1970s, initially proposing we could warm Venus or Mars by altering their atmospheres. But Venus, with its crushing surface pressure and sulfuric acid clouds, proved far too hostile. Mars became the prime candidate. Now, think about this carefully. Every breath you take contains nitrogen and oxygen in just the right proportions. The temperature outside, whether it's summer or winter, stays within a range that allows liquid water to exist. Earth's magnetic field protects you from lethal radiation. All of these factors exist in a delicate balance that took billions of years to achieve naturally. To terraform Mars, we need to recreate this balance artificially, and we need to do it in a time frame measured in human lifetimes rather than geological epochs. The audacity of this goal cannot be overstated. Let's start with the atmosphere, because without solving this problem, everything else is pointless. Right now, Mars's atmosphere is about 1% as dense as Earth's. If you stood on Mars without a spacesuit, you wouldn't just suffocate from lack of oxygen. The low pressure would cause the liquids in your body to vaporize. Your blood would literally boil at body temperature, a horrifying process called ebullition. You'd lose consciousness in 15 seconds and be dead within 2 minutes. Any plan to terraform Mars must begin by thickening this atmosphere dramatically. Here's where it gets fascinating. Mars actually has plenty of carbon dioxide trapped in various reservoirs. The polar ice caps contain frozen carbon dioxide, dry ice that glitters under the Martian sun. The regolith, the dusty soil that covers Mars, holds carbon dioxide absorbed into its minerals. And according to data from NASA's MAVEN spacecraft, the Martian soil may contain vast amounts of carbon dioxide locked away in carbonates. If we could release this carbon dioxide into the atmosphere, we could trigger a greenhouse effect, the same phenomenon that's warming Earth, but on Mars, we'd be doing it intentionally and beneficially. Imagine this scenario. We begin by deploying thousands of satellites equipped with mirrors, massive reflective surfaces positioned in orbit around Mars. These mirrors, each the size of several football fields, would focus and redirect sunlight onto Mars's polar ice caps. The concentrated solar energy would warm the poles, causing the frozen carbon dioxide to sublimate, transforming directly from solid to gas without becoming liquid. As this carbon dioxide enters the atmosphere, it begins to trap heat. The temperature rises. As the temperature rises, more ice melts, releasing more carbon dioxide. This is what scientists call a positive feedback loop, a cascading effect where each change amplifies the next. But here's a critical question you should ask yourself. Who decides when to start this process? What international body has the authority to begin reshaping another planet? We haven't even agreed on how to govern Antarctica or the deep oceans, and those are on Earth. Now we're talking about planetary engineering on a world that, according to the Outer Space Treaty of 1967, belongs to no one and everyone simultaneously. The political and ethical dimensions of terraforming are as complex as the technical challenges. Some scientists have proposed even more aggressive methods to warm Mars. The aerospace engineer Robert Zubrin, one of the most passionate advocates for Mars colonization, has suggested we could manufacture super greenhouse gases on Mars's surface. These are compounds like perfluorocarbons that trap heat far more efficiently than carbon dioxide. A relatively small amount of these gases could have an outsized warming effect. We could potentially manufacture these gases using automated factories powered by nuclear reactors, sending them into the atmosphere in a controlled release. Within decades, not centuries, we might raise Mars's temperature by tens of degrees. Then there's the nuclear option, and I mean that literally. Elon Musk, the entrepreneur behind SpaceX, famously suggested we should nuke Mars during an appearance on a late-night talk show. What he meant, though it sounds like the plot of a disaster movie, is that we could detonate nuclear weapons above Mars's polar caps to instantly vaporize massive amounts of frozen carbon dioxide. The explosions wouldn't contaminate the surface because they'd be airburst detonations, and the sudden injection of greenhouse gases could jumpstart the warming process. However, most planetary scientists consider this approach too crude, too unpredictable, and too risky. The radiation from even airburst nuclear explosions could have unforeseen consequences for the Martian environment and any future colonists. Picture Mars a century from now under any of these scenarios. The average temperature has risen from -80 degrees to perhaps -20 degrees Fahrenheit. It's still bitterly cold by Earth standards, but liquid water could exist during the day in equatorial regions. The atmospheric pressure has doubled or tripled, still far too thin to breathe, but thick enough that you'd only need an oxygen mask rather than a full pressure suit. The sky is beginning to change color as more atmosphere scatters light differently. This is just the beginning. Now we face an even more daunting challenge. Mars has no magnetic field, or rather, it has only weak remnants of one embedded in its crust. Earth's magnetic field is generated by our planet's liquid iron outer core, which acts like a giant dynamo as it churns and flows. Mars's core cooled and solidified billions of years ago, killing its magnetic field. Without this invisible shield, the solar wind, that stream of charged particles flowing from the sun, strikes Mars's atmosphere directly. Over time, it strips away atmospheric particles, atom by atom, molecule by molecule. NASA's MAVEN mission confirmed that Mars is still losing atmosphere to the solar wind today, though at a much slower rate than in the ancient past. Here's the terrifying implication. Even if we successfully thicken Mars's atmosphere, it would gradually erode away again. We'd be filling a bucket with a hole in the bottom. Some estimates suggest that a newly created Martian atmosphere might last tens of thousands of years before being significantly depleted, which sounds like a long time but is merely an eye blink in geological terms. We'd need to constantly replenish the atmosphere, essentially committing future generations to maintaining a planet on life support forever. Unless, and this is where we enter the realm of truly advanced speculation, we could give Mars an artificial magnetic field. In 2017, NASA's Planetary Science Division Director Jim Green presented a fascinating concept at a workshop. He proposed positioning a massive magnetic dipole, essentially a giant superconducting electromagnet, at the Mars-Sun Lagrange point, a stable position between Mars and the Sun where gravitational forces balance out. This artificial magnetic shield would deflect the solar wind around Mars, protecting any atmosphere we create. Think about the engineering challenge this represents. We'd need to construct and position a magnetic field generator powerful enough to shield an entire planet, maintain it in a precise orbital position, and ensure it functions for centuries. The superconducting magnets would need to operate at incredibly cold temperatures, which, ironically, wouldn't be a problem in the cold of space, and they'd need a power source that could function reliably for longer than any human technology has ever operated. We're talking about infrastructure that must outlast empires, religions, and perhaps even languages. But let's say, hypothetically, we solve these problems. Let's say that a century or two into our terraforming project, Mars has a thicker atmosphere, higher temperatures, and even an artificial magnetic shield. We've transformed Mars from a -80-degree near vacuum into a -20-degree environment with survivable atmospheric pressure. What comes next? Life. Not human life. Not yet. The atmosphere still has almost no oxygen. It's mostly carbon dioxide with some nitrogen. You still can't breathe it. But this is where we could introduce the ultimate terraforming tool: biology. Life transformed Earth from a toxic, oxygen-free world into the blue-green paradise we know today. Could we use life to do the same on Mars? Enter extremophiles, organisms that thrive in conditions that would kill most life. In Earth's polar regions, deserts, deep ocean vents, and underground caves, scientists have discovered bacteria and archaea that survive extreme cold, intense radiation, high salinity, and minimal water. Some organisms called cyanobacteria, the same ancient life forms that first oxygenated Earth's atmosphere billions of years ago, might be engineered to survive on Mars. They could use photosynthesis to convert carbon dioxide into oxygen while building organic matter from Martian minerals. Picture this: autonomous biological factories, domes filled with genetically modified organisms designed specifically for Martian conditions. They would be our tireless workers, breathing in carbon dioxide and exhaling oxygen, spreading across the Martian landscape wherever liquid water exists. We might engineer hardy lichens, symbiotic partnerships between fungi and photosynthetic partners, adapted to extreme UV radiation and low temperatures. These pioneers would begin the slow process of creating soil, that complex mixture of minerals and organic matter that Earth's plants depend on. But here's an ethical question that should make you pause. Do we have the right to introduce Earth life to Mars, even if we found no evidence of current Martian life? What if microbial life exists deep underground in Martian aquifers, clinging to existence in the last refuges of liquid water? Would we be committing genocide against an entire biosphere we never bothered to fully explore? Some scientists argue we should thoroughly search Mars for any signs of indigenous life before we even consider terraforming. Others counter that if Martian life exists, it's been surviving for billions of years and could likely coexist with Earth organisms, or that we could preserve certain regions as protected wilderness areas. There's another consideration that rarely gets discussed in popular accounts of terraforming: the sheer amount of material we might need to import to Mars. While Mars has carbon dioxide, nitrogen is another story. Earth's atmosphere is 78% nitrogen, an essential element for life and a necessary buffer gas in any breathable atmosphere. Mars has very little nitrogen. Data from NASA's Curiosity rover suggests that most of Mars's nitrogen may have been lost to space along with its atmosphere billions of years ago. If Mars doesn't have enough nitrogen, we'd need to import it. Where would it come from? Some scientists have suggested we could redirect comets or asteroids rich in nitrogen compounds to impact Mars. A controlled bombardment of icy bodies from the outer solar system could deliver both nitrogen and water to Mars. Each impact would release enormous energy, warming the planet and adding volatiles to the atmosphere. But weaponizing asteroids and comets carries obvious risks. An error in calculation could send a massive object crashing into a populated Martian settlement, causing destruction on a scale that would make any Earth disaster pale in comparison. Others have proposed we could mine nitrogen from Titan, Saturn's largest moon, which has a thick nitrogen atmosphere. But Titan is nearly 800 million miles from Mars at closest approach. The logistics of mining Titan's atmosphere and transporting it to Mars boggle the mind. We'd be creating an interplanetary supply chain spanning the solar system, a level of infrastructure that presupposes an advanced spacefaring civilization we're nowhere close to becoming. Let's assume, for the sake of our thought experiment, that we've overcome all these challenges. Several centuries into the future, Mars has a thicker atmosphere with more nitrogen and oxygen. The temperature in equatorial regions rises above freezing during summer days. Liquid water flows seasonally on the surface. Engineered organisms have spread across significant portions of the planet, creating primitive soil and continuing to convert atmospheric carbon dioxide into oxygen. The sky is transitioning from pink to a purplish blue as the atmosphere thickens and its composition changes. This is where we could begin introducing more complex plant life. Starting with the hardiest species, perhaps Arctic mosses and grasses adapted to cold climates, then gradually introducing shrubs, eventually trees. Imagine forests of specially adapted pine trees spreading across the Martian plains, their roots breaking up the regolith, their needles adding organic matter to the developing soil. Picture valleys where liquid water flows for months at a time, lined with vegetation that's never existed before, hybrid species engineered to combine the hardiness of extremophiles with the productivity of earth plants. But the timeline for this process is sobering. Even with aggressive intervention, most scientific models suggest it would take at minimum 500 to 1,000 years to create a breathable atmosphere on Mars through biological processes alone. And that's assuming everything goes according to plan, which, given the scale and complexity of terraforming, seems wildly optimistic. More conservative estimates suggest it could take 10,000 years or more. That's longer than all of recorded human history. Consider what this means. If we started terraforming Mars today, with the most aggressive possible timeline, the first person to take an unassisted breath of Martian air hasn't been born yet. Neither have their parents, grandparents, or great-grandparents. We'd be initiating a project that would span dozens of human generations, requiring continuous commitment, resources, and effort from societies we can't even imagine. Governments, corporations, and nations have risen and fallen in shorter time frames. The entire modern scientific method is only about 400 years old. We're talking about a commitment that dwarfs anything humanity has ever attempted. This raises profound philosophical questions about our obligations to the future. Would people 500 years from now thank us for beginning this process, or curse us for committing their resources to a project they might not want to continue? What if human civilization on Earth collapses due to climate change, war, or some unforeseen catastrophe? Would the Mars colony survive independently, or would the entire terraforming project grind to a halt, leaving Mars in some liminal state, neither the pristine world it was nor the habitable planet it was meant to become. And here's something that should chill you to your core. What if we're successful? What if we terraform Mars, and thousands of years from now, there are two human civilizations, one on Earth and one on Mars, separated by tens of millions of miles and months of travel time, even with advanced propulsion. History shows us that when populations split and develop independently, they diverge. Languages change. Cultures evolve differently. Political interests clash. Would Earth and Mars eventually go to war? Would we export humanity's worst tendencies, our tribalism and violence, to the cosmic stage? There's another scenario, more optimistic but equally strange. What if the process of terraforming Mars transforms us? Not just technologically, but fundamentally, as a species? The level of global cooperation, long-term planning, and resource management required to terraform a planet would necessitate solving many of Earth's current problems. We'd need to achieve sustainable energy production, closed-loop life support systems, and efficient resource utilization. The technologies developed for terraforming Mars could help us better manage Earth's ecosystems. Some philosophers and futurists argue that working toward a long-term goal like terraforming Mars could unite humanity in ways nothing else could. When you're part of a multi-generational project to create a new biosphere, petty national disputes seem less important. The overview effect, that cognitive shift reported by astronauts who see Earth from space and realize how fragile and unified our planet is, might extend to species-level thinking. We might begin to see ourselves as a spacefaring civilization rather than competing nations. But let's zoom back to the practical realities, because between our current moment and that speculative future lie enormous technical hurdles we haven't even touched on. Water is one of the most critical resources for any terraformed Mars, and while we know Mars has water ice, most of it is locked up in the polar ice caps or buried in the regolith. To have rivers, lakes, and eventually oceans on Mars, we'd need to melt and redistribute this water. Current estimates suggest Mars has enough water ice to cover the entire planet in an ocean 35 meters deep if it all melted. That might sound like a lot, but remember that Earth's oceans average about 4,000 meters deep. Mars would have shallow seas at best, probably concentrated in the northern lowlands where the elevation is lowest. And there's a catch. Melting all this ice would require enormous amounts of energy and sustained temperatures above freezing. As Mars warms and the atmospheric pressure increases, some of this ice would naturally sublimate or melt. But we might need to actively excavate and melt ice deposits, pump liquid water to create initial lakes and reservoirs, and maintain these water bodies until the climate stabilizes enough to sustain them naturally. We're essentially creating a planetary plumbing system, managing water resources on a scale that makes Earth's largest water management projects look like children playing with garden hoses. And water on Mars presents unique challenges. Martian regolith contains perchlorates, toxic chemical compounds that can damage human thyroid function and have other harmful effects. If we melt ice that's been in contact with this regolith, we'd have toxic water. We'd need massive filtration and purification systems, or we'd need to bioremediate the soil, using specially adapted organisms to break down or sequester perchlorates. The idea of a pristine Martian stream is lovely, but the reality would likely involve centuries of environmental cleanup before the water was safe for Earth-like ecosystems. Here's something most people don't realize about terraforming. It's not a one-way process that steadily improves Mars. There would be setbacks, failures, and possibly catastrophes. Imagine we've created a thin but growing atmosphere, and then Mars experiences one of its global dust storms, events that can envelope the entire planet for months. These storms could disrupt power generation from solar panels, reduce temperatures by blocking sunlight, and generally wreak havoc on a developing ecosystem. Or imagine a massive asteroid impact on our partially terraformed Mars. The devastation could undo centuries of work in an instant. This is why any realistic terraforming plan would need redundancy built into every system. We couldn't rely on a single method of atmospheric generation or warming. We'd need multiple independent processes happening simultaneously, so that if one fails, others continue. We'd need robust monitoring systems, disaster response plans, and the flexibility to adapt as unexpected challenges arise. It would be, without exaggeration, the most complex and long-term project management challenge ever undertaken. Now let me paint you a picture of what a partially terraformed Mars might look like, say 300 years into an aggressive terraforming program. In the equatorial regions, especially in the lowlands of Hellas Planitia or the northern plains, the atmospheric pressure has reached about 30% of Earth's at sea level. That's roughly equivalent to the pressure at the summit of Mount Everest. The temperature during summer days can reach 50 degrees Fahrenheit, though it still plunges well below freezing at night and during winter. Water flows in seasonal streams, fed by melting subsurface ice. Hardy engineered plants the landscape, clustering around these water sources. The sky is a strange mauve color, not quite pink anymore, but not the blue of Earth. Humans still need oxygen masks and some thermal protection, but they can walk on the surface wearing something closer to high-altitude mountaineering gear than full spacesuits. Cities under protective domes house millions of people, and there's active debate about whether to continue the terraforming process or maintain Mars in this intermediate state. Because here's a question that would likely arise. At what point is Mars terraformed enough? Do we need a planet identical to Earth, or would a Mars where humans need minimal assistance be acceptable? Some argue that a partially terraformed Mars, requiring only an oxygen mask rather than full life support, might be the optimal goal. It would be achievable in a much shorter time frame, maybe a few centuries rather than millennia. It would preserve more of Mars's unique characteristics, and it would be easier to maintain, requiring less energy and resources to sustain. Others would argue that anything less than a fully Earth-like planet is failure. Why commit to centuries of effort only to create a world where humans still can't breathe freely? Why not push for the complete transformation? This debate would likely rage through generations of Martian colonists and Earth-based planners, and different factions might support different approaches, potentially leading to political conflicts over the planet's future. There's another approach to terraforming that we should explore, one that's rarely discussed in popular media but that some scientists consider more practical: para-terraforming. Instead of transforming the entire planet, we could create large enclosed habitats, essentially massive domes or underground caverns where Earth-like conditions are maintained. These habitats could be expanded over time, gradually spreading across Mars's surface. The advantage of para-terraforming is that it's more achievable with current or near-future technology. We wouldn't need to solve the magnetic field problem or import massive amounts of nitrogen. Each habitat would be a controlled environment where we could optimize conditions for human life. The disadvantage is obvious. You're not creating a second Earth. You're creating a series of enclosed environments on a still hostile planet. It's essentially a compromise position, acknowledging that full terraforming might be impossible or impractical while still allowing for large-scale colonization. But imagine a Mars dotted with hundreds or thousands of these habitats, connected by underground tunnels and surface transit tubes. Each dome could contain different ecosystems, experimental forests, agricultural zones, residential areas. Over centuries, these domes could potentially be merged, linked together to form larger and larger pressurized zones. Eventually, you might have regions of Mars hundreds of square kilometers in area under breathable atmosphere, even if the planet as a whole remains untransformed. This hybrid approach, combining para-terraforming with gradual planetary terraforming, might be the most realistic path forward. Start with domes and enclosed habitats to establish a foothold. Use these initial colonies to produce the infrastructure for larger-scale atmospheric manipulation. As the planetary atmosphere slowly thickens and warms, the domes become easier to maintain and can grow larger. Centuries or millennia down the line, the distinction between dome and open atmosphere becomes less clear as the gaps between habitats are filled in. Now we need to talk about something crucial that's often overlooked. Who actually does all this work? The romantic vision of terraforming often features brilliant scientists and brave explorers heroically reshaping a planet. The reality would be far more mundane and industrial. Terraforming would require massive amounts of manual labor, industrial processing, mining, construction, and maintenance. You'd need millions of workers, initially robots and automation, but eventually humans as well, dedicating their lives to tasks like mining regolith for resources, operating atmospheric processors, maintaining equipment, building infrastructure. It would be, in many ways, similar to the Industrial Revolution, with all the social and economic implications that entails. Would these workers be fairly compensated? Would there be exploitation? How would labor rights work on Mars? There's a disturbing historical parallel worth considering. Many of Earth's grandest projects were built on the backs of enslaved or exploited labor. The pyramids, the Great Wall, much of the infrastructure of colonial empires. Will we repeat these patterns on Mars? Some science fiction authors have explored dystopian visions of Mars colonization where indentured servants work off their passage to Mars, essentially becoming slaves to corporations or governments. Others imagine more utopian scenarios where automation handles most of the dangerous work, and humans focus on planning and oversight. The economic model for terraforming Mars is also deeply unclear. Who funds a project that will take centuries to complete and may never show a traditional return on investment? Governments could fund it, but government priorities change with elections and public opinion. Private corporations lack the incentive to invest in projects that won't be profitable for generations. Some have proposed international consortiums, pooling resources from multiple nations and private entities, but coordinating such an effort across centuries seems politically impossible. There's another possibility, more speculative but worth considering. What if advanced artificial intelligence becomes the driving force behind terraforming? AI systems, unlike humans, could potentially maintain focus on multi-century goals without being distracted by short-term concerns. An AI designed to terraform Mars could operate automated systems, optimize resource allocation, and adapt to challenges over timescales that exceed human lifespans. Of course, this raises its own ethical questions about creating AI systems with such power and long-term autonomy. Let's talk about something that might change everything we've discussed so far. The possibility that we're fundamentally wrong about how to terraform Mars, that there's a much faster or easier method we haven't discovered yet. Science and technology don't progress linearly. They advance in leaps when paradigm-shifting discoveries are made. What if someone discovers a way to rapidly generate a magnetic field around Mars using principles we don't yet understand? What if we find exotic materials or energy sources that make atmospheric manipulation orders of magnitude easier? Throughout history, technological limitations that seemed absolute were overcome by unexpected breakthroughs. Powered flight was considered impossible until it wasn't. Splitting the atom was theoretical until it became devastatingly real. Computers were room-sized machines until they fit in our pockets. Could there be a similar breakthrough waiting in our understanding of planetary science? One that makes terraforming Mars not a 1,000-year project but a century-long one? Recent discoveries about Mars have already changed our understanding multiple times. In 2018, the European Space Agency's Mars Express orbiter detected evidence of a subsurface lake of liquid water beneath the Martian south polar ice cap. This discovery excited scientists because liquid water could potentially harbor life and would also be a crucial resource for terraforming. Then, in subsequent years, more detailed analysis suggested there might be multiple subsurface lakes. If Mars has accessible liquid water reserves beneath its surface, that dramatically changes the resource equation for terraforming. Similarly, measurements from NASA's InSight lander, which studied Martian seismic activity and internal structure, have given us better data about Mars's core and interior heat. This information is crucial for understanding whether Mars might have any remaining geothermal energy that could be harnessed. It also helps us model how artificially generated heat might spread through the Martian subsurface. Every new mission to Mars adds pieces to the puzzle. And sometimes those pieces reveal the puzzle is different than we thought. Here's a mind-bending possibility. What if we're already terraforming Mars accidentally? Every probe and rover we've sent to Mars carried Earth microbes despite our best sterilization efforts. Sterilization protocols are good but not perfect. It's entirely possible that hardy Earth bacteria are already surviving in Martian environments, perhaps in the relatively warm interior of our robotic explorers or in protected microenvironments on the Martian surface. If these organisms are reproducing and spreading, they're beginning to alter Mars, however slightly, right now. This accidental contamination horrifies planetary protection scientists who want to preserve Mars in its pristine state for scientific study. But it also raises an interesting question. If Earth life can survive on Mars without extensive terraforming, does that change our calculus? Some scientists have suggested we should study how these organisms adapt to Martian conditions, as they might teach us valuable lessons about what kinds of life could be intentionally introduced during terraforming. Now I want to explore some of the more exotic and speculative terraforming proposals, ideas that push the boundaries of known science and engineering. One proposal involves using massive orbital mirrors to focus sunlight on Mars, but not just to melt polar ice. The mirrors could be positioned to extend the effective length of Martian days in certain regions, providing more hours of light for photosynthetic organisms. They could also direct light into deep canyons and craters that are normally shadowed, creating warm microclimates in otherwise cold regions. Another wild idea. What if we could manufacture a temporary artificial atmosphere while we work on creating a permanent one? Some engineers have proposed deploying a fleet of satellites that would continuously release gases into Mars's upper atmosphere, maintaining a thicker blanket of air through constant replenishment. This would be enormously expensive and energy-intensive, essentially running the atmospheric equivalent of a treadmill, but it might allow us to create breathable pockets of atmosphere around settlements much faster than whole-planet terraforming. There's also the concept of using Martian moons Phobos and Deimos as resource bases or even as weapons in the terraforming process. Phobos orbits so close to Mars that it's gradually spiraling inward and will eventually either crash into Mars or break apart into a ring system. Some have proposed we could accelerate this process, deliberately deorbiting Phobos in a controlled manner so that it impacts Mars in a specific location. The energy from such an impact would be staggering, potentially warming Mars significantly and ejecting material into the atmosphere. Of course, this would also create a crater hundreds of kilometers across and trigger global dust storms, so it's not a gentle option. Let me pause here and ask you to consider. As you hear these proposals, ranging from the plausible to the fantastical, how do you feel about our species having this level of power? We're talking about deliberately crashing moons, engineering climates, reshaping entire atmospheres. This is power on a scale that would have been considered godlike to our ancestors. Does this excite you with possibilities or terrify you with the potential for catastrophic mistakes? The philosophical and psychological implications of terraforming extend beyond the technical challenges. There's a concept in environmental psychology called solastalgia, the distress caused by environmental change to one's home environment. Imagine being born on Mars in the early stages of terraforming. The Mars you grow up on is different from the Mars your parents knew, and it's different from the Mars that will exist when your children are grown. The landscape, the sky, the very air around you is constantly changing on timescales observable within a human lifetime. This could be profoundly disorienting. On Earth, we expect certain constants. The color of the sky, the feel of rain, the sound of wind. On a terraforming Mars, nothing would be constant. Each generation would experience a fundamentally different world. This might create a unique Martian psychology, a culture adapted to constant change and transformation. Or it might create deep psychological stress and a longing for stability that can never be achieved. There's also the question of identity. When does a human being born on Mars stop being a Martian colonist and become simply a Martian? When does Mars stop being a project and become a home? These aren't academic questions. They have real implications for how people relate to the planet and the terraforming process. Will future Martians be grateful for the transformation their ancestors initiated? Or will some faction arise that wants to halt terraforming and preserve Mars in whatever state it exists when they're born? Science fiction has explored this question through various narratives of Martian independence movements and conflicts between Earth and Mars over the planet's fate. While fiction, these stories raise legitimate concerns about governance and self-determination. If Mars develops its own indigenous population, do they have the right to decide their planet's future, even if that means halting or reversing terraforming efforts funded by Earth? What if Earth-based interests want to continue terraforming, but Martian residents want to stop? Who has the final say over a planet's destiny? Let's shift our focus to the scientific payoff of terraforming Mars, beyond the obvious benefit of creating a second home for humanity. The process of terraforming would teach us an enormous amount about planetary science, atmospheric physics, ecology, and bioengineering. We'd essentially be running the largest controlled experiment ever conceived, testing our understanding of how planets and biospheres work. This knowledge could be invaluable for managing Earth. Right now, humanity is inadvertently running an uncontrolled experiment on Earth's climate through greenhouse gas emissions and other environmental impacts. We're not sure exactly how Earth's complex systems will respond, which is why climate modeling is so challenging. If we successfully terraform Mars, we demonstrate a much more sophisticated understanding of planetary systems, and we could potentially apply this knowledge to better manage or even restore Earth's environment. Imagine if terraforming research led to breakthroughs in carbon sequestration, allowing us to efficiently remove carbon dioxide from Earth's atmosphere. Or if it led to better understanding of how to restore damaged ecosystems, reverse desertification, or green the Sahara. The knowledge gained from transforming Mars could help us heal Earth. In a strange way, the project to create a second home for humanity might teach us how to better care for our first home. There's another scientific benefit that's rarely discussed: Mars as a laboratory for studying planetary evolution. By observing how Mars responds to our interventions, we'd learn about the processes that shaped all rocky planets, including Earth. We might gain insights into why Venus became a hellish greenhouse while Mars became a frozen desert. We could test theories about planetary habitability and the conditions necessary for life. This knowledge would inform our search for habitable exoplanets around other stars and help us interpret the data we're gathering from telescopes like the James Webb Space Telescope. Speaking of exoplanets, terraforming Mars would be humanity's first step toward becoming a multiplanetary and eventually interstellar species. The technologies, social structures, and knowledge base we develop while terraforming Mars would be applicable to colonizing other worlds. If we can terraform Mars, we could potentially terraform Venus, though that would be even more challenging. We could establish colonies on the moons of Jupiter or Saturn, creating habitats in environments far more hostile than Mars. Eventually, we might even terraform planets around other stars. This is where the narrative of terraforming Mars connects to the grandest possible vision of humanity's future. Are we destined to remain on Earth, the only known planet with life, until some catastrophe befalls us? Or do we spread outward, ensuring the survival of Earth life and human consciousness throughout the galaxy? Terraforming Mars is the first real test of whether we're capable of the latter. But let's ground ourselves in current reality, because the path from here to terraforming Mars is not clear or certain. Right now, we've barely begun to establish a permanent human presence beyond Earth. The International Space Station represents our most advanced off-world outpost, and it houses only a handful of people at a time, completely dependent on regular resupply from Earth. We haven't sent humans beyond low Earth orbit since the Apollo program ended in 1972. We haven't even established a permanent base on our own moon, which is orders of magnitude easier to reach than Mars. Before we can terraform Mars, we need to establish a self-sustaining colony there, and that alone is a monumental challenge. Getting humans to Mars is difficult but achievable with current technology. Keeping them alive and productive once they're there is harder. Creating a settlement that can survive without constant support from Earth, that can grow its own food, manufacture its own equipment, and expand its population is harder still. We need to walk before we can run, and we're still learning to crawl in terms of becoming a spacefaring species. SpaceX's Starship, Blue Origin's lunar ambitions, NASA's Artemis program, and Chinese plans for lunar and Martian exploration represent genuine progress toward establishing off-world colonies. But there's an enormous gulf between landing astronauts on Mars for brief visits and building the industrial infrastructure necessary to begin terraforming. We're talking about establishing not just a base but an entire civilization on Mars, with millions of people, extensive manufacturing capability, and the resources to undertake planetary engineering. The timeline for this is uncertain. Optimists like Elon Musk have suggested we could have humans on Mars by the late 2020s or early 2030s, with a self-sustaining city following in subsequent decades. Skeptics point to the repeated delays in space programs and the enormous technical challenges remaining, suggesting that a Martian city is still a century or more away. The truth likely lies somewhere in between, dependent on factors we can't fully predict: political will, economic conditions, technological breakthroughs, and perhaps most importantly, whether the initial Martian settlers can actually thrive rather than merely survive. Here's something sobering to consider. Every astronaut who has spent extended time in space has experienced bone density loss, muscle atrophy, vision problems, and other health effects from microgravity and radiation exposure. Mars has only 38% of Earth's gravity. We don't actually know what long-term health effects living in Martian gravity will have because no human has ever experienced it. It's possible that humans born on Mars would develop normally. It's also possible they'd have serious health problems, weakened bones and muscles, cardiovascular issues, or developmental challenges. If humans can't actually thrive in Martian gravity, then the entire premise of terraforming becomes questionable. What's the point of creating a breathable atmosphere on a planet where humans can't maintain their health? We might need to solve the gravity problem first, perhaps through rotating habitats that generate artificial gravity through centrifugal force, or through medical interventions like gene therapy or pharmaceutical treatments that prevent bone and muscle loss. We're adding yet another layer of complexity to an already staggeringly complex project. Radiation is another major concern. Earth's magnetic field and thick atmosphere protect us from cosmic radiation and solar particle events. Mars, with its thin atmosphere and weak magnetic field, offers little protection. Long-term exposure to this radiation would increase cancer risk, potentially cause neurological damage, and could render colonists sterile or cause genetic damage that affects their children. Even if we terraform Mars's atmosphere, without solving the magnetic field problem, radiation would remain a serious health hazard. Some proposed solutions include building underground cities on Mars, using the regolith itself as radiation shielding. Cities could be carved into cliff faces or canyon walls, built in lava tubes, or simply buried beneath meters of Martian soil. This would protect residents from radiation but would also mean living underground, potentially never seeing the sky you've worked so hard to transform. It's a grim irony. We terraform the surface to make it habitable, but we have to live underground to stay healthy. Unless, and this circles back to the artificial magnetic field concept, we can shield the entire planet. If that's possible, and it's a significant if, then terraforming becomes much more attractive. You'd have both a breathable atmosphere and protection from radiation. But until we develop and deploy such technology, Martian colonists would face difficult choices about where and how to live. Let's talk about the resources required for terraforming on a more concrete level. One estimate suggested that warming Mars using orbital mirrors would require mirrors with a total surface area of thousands of square kilometers. Manufacturing and deploying such structures would require mining operations on a scale never before attempted. We'd likely need to source materials from asteroids or Martian moons rather than launching them from Earth, as the cost of lifting material out of Earth's gravity well is prohibitively expensive. This means we'd need to establish asteroid mining operations and orbital construction facilities before we could even begin serious terraforming. We're talking about an entire space-based economy and industrial complex as a prerequisite for terraforming. The infrastructure required to build the infrastructure required to terraform Mars is itself a multi-generational project. The energy requirements are equally staggering. Running atmospheric processors, powering settlements, operating manufacturing facilities, all while slowly warming a planet would require enormous amounts of energy. Solar power would be less efficient on Mars than on Earth due to the greater distance from the Sun, though it would still be viable. Nuclear power, either fission or potentially fusion if we develop it, would likely be necessary. We might need hundreds or thousands of nuclear reactors on Mars to provide sufficient power. And here's a question that should make you think. What happens when something goes wrong with these systems? On Earth, a nuclear accident like Chernobyl or Fukushima is a regional disaster. On a partially terraformed Mars with millions of inhabitants dependent on continuous operation of life support and terraforming systems, a major malfunction could be catastrophic. The margin for error would be razor thin. We'd need multiple redundant systems, fail-safes, and disaster response capabilities far beyond anything we currently possess. Risk management for planetary terraforming would be its own field of study. Imagine trying to calculate the probability of various failure modes and their consequences when you're dealing with systems that have never been built before, operating at scales never attempted, over time spans longer than recorded history. How do you plan for contingencies centuries in advance? How do you design systems that can be maintained and upgraded by future generations who may have different technologies and priorities than the original designers? There's also the question of unintended consequences. Earth's history is full of examples of ecological interventions that went catastrophically wrong. Species introduced to control pests become pests themselves. Engineering projects cause unforeseen environmental damage. Medications have side effects nobody predicted. Now imagine these problems on a planetary scale. What if the organisms we introduce to Mars evolve in unexpected ways? What if our atmospheric manipulation triggers unforeseen chemical reactions? What if warming Mars releases subsurface gases we didn't know were there, creating a runaway greenhouse effect or toxic atmosphere? We'd need incredibly sophisticated monitoring and modeling capabilities, able to track billions of variables across an entire planet and predict how they might interact. Even then, we'd be operating on incomplete information, making educated guesses about systems we don't fully understand. The first generation of terraformers would essentially be feeling their way forward in the dark, learning through trial and error but unable to undo mistakes that might take centuries to manifest fully. Let me paint you a different kind of picture now, one that's less about technical challenges and more about the human experience. Imagine you're part of the 100th generation of Martian settlers, living roughly 2,000 years into the terraforming project. Your ancestors left Earth so long ago that their world is almost mythical to you. You've grown up in a Mars that has oceans in the northern lowlands, forests around the equator, and a sky that's unmistakably blue during the day, though it still shows strange colors at sunset as the remaining dust in the atmosphere catches the light. You can walk outside without an oxygen mask in many regions, though the air is still thin and you tire quickly with exertion. The temperature is cool but not unbearable, similar to a cold autumn day in Earth's temperate zones. Around you, a civilization of hundreds of millions spans the planet, with great cities, agricultural regions, wild areas that have been seeded with Earth life and are evolving into unique Martian ecosystems. But you also know that maintaining this paradise requires constant work. The atmosphere still needs replenishment as solar wind strips away some of it despite the artificial magnetic shield. The climate systems aren't fully self-regulating yet. Some organisms thrive in ways nobody predicted and need to be controlled. Others fail to establish and need to be reintroduced. You're part of a civilization that's as much gardener as inhabitant, constantly tending to the planet you call home. You might look at Earth through a telescope and see the blue world your species came from, and feel a complex mix of emotions. Connection, because that's your ultimate origin. Separation, because Mars is your home in a way Earth never could be. Perhaps some resentment, because Earth still has so much natural beauty and habitability that Mars required millennia of effort to partially recreate. Or perhaps gratitude, that your ancestors had the vision and courage to begin this grand project. This is the human story of terraforming, the lived experience that statistics and timelines can't fully capture. It's about people dedicating their lives to a project bigger than themselves, working toward a goal they'll never fully see realized, but finding meaning in that work nonetheless. It's about the slow accumulation of small changes into transformation, about patience and persistence on timescales that challenge our very conception of progress. Now let's explore one of the most controversial aspects of terraforming: the question of whether we should do it at all. There's a growing movement of planetary preservationists who argue that Mars should be left in its natural state, that we have no right to transform another planet regardless of our ability to do so. They point out that Mars has scientific value as a pristine example of planetary evolution, that we've already caused massive environmental damage on Earth and shouldn't repeat our mistakes elsewhere, and that there may be intrinsic value in wilderness, even alien wilderness. These arguments deserve serious consideration. Mars is the only other planet in our solar system where we can study geological processes similar to Earth's, see what a planet looks like without life's influence, and potentially discover evidence of how life begins or fails to begin. Once we terraform Mars, we destroy this natural laboratory forever. We can't undo it. If we later decide we made a mistake, it's too late. The pristine Mars will be gone, transformed irrevocably. There's also the possibility, however remote current evidence suggests it might be, that Mars harbors life or once harbored life in the geologically recent past. If we terraform Mars before thoroughly searching for such life, we might destroy it before we ever discover it. This would be an act of cosmic vandalism, erasing evidence of one of the most profound questions in science. Are we alone in the universe? On the other hand, advocates for terraforming argue that while Mars has scientific value, Earth's survival and the survival of Earth life has practical value. If humanity remains confined to one planet, a single catastrophic event could wipe us out entirely. An asteroid impact, a nuclear war, a pandemic, or runaway climate change could end the only known instance of intelligent life in the universe. Terraforming Mars provides insurance, a backup for Earth's biosphere and human civilization. They also argue that transformation isn't inherently bad. Earth itself has been transformed many times by geological processes, asteroid impacts, and the evolution of life itself. The oxygen we breathe is the waste product of ancient cyanobacteria. Should that transformation of Earth's atmosphere be considered wrong? If not, why is deliberately transforming Mars different? Is intentionality the issue? Or is there something special about natural processes that makes their effects more acceptable than deliberate engineering? This philosophical debate connects to deeper questions about humanity's role in the universe. Are we caretakers, obligated to preserve what exists? Are we transformers, meant to spread and reshape according to our needs? Or are we something else entirely, perhaps explorers and students meant to observe and learn without interference? Different ethical frameworks and worldviews lead to different conclusions, and there's unlikely to be universal agreement. A compromise position suggests we should conduct thorough scientific exploration of Mars first, searching extensively for any signs of current or past life. If none is found after decades of intensive study, and if we've learned everything we can from pristine Mars, then we might consider beginning cautious, reversible terraforming efforts. Start small, observe the effects, and only proceed if we're confident we understand what we're doing. This approach is more conservative, but also more time-consuming and uncertain. There's another fascinating angle to consider. What if terraforming Mars actually helps us find Martian life? Bear with me here. If microbial life exists deep underground in Martian aquifers, we might never find it with surface rovers and limited drilling. But if we warm Mars and increase its atmospheric pressure, we might bring subsurface water closer to the surface or even create conditions where underground water wells up naturally. This could expose any subsurface life to our detection. Of course, this exposure might also endanger such life by introducing Earth organisms or changing Martian conditions. But some scientists argue we might be more likely to discover Martian life through the process of terraforming than through conservative exploration. It's a controversial idea, and planetary protection advocates generally reject it, but it highlights the complex trade-offs we face. Let's talk about the cultural and artistic implications of terraforming Mars. The process would inspire art, literature, music, and philosophy on an unprecedented scale. Imagine documentary filmmakers capturing the first engineered rainstorm on Mars, artists painting the changing Martian skies, poets finding words for the experience of watching a dead world come to life. The terraforming of Mars would be humanity's greatest creative project as well as its greatest engineering achievement. Future Martian cultures would develop their own holidays and traditions around terraforming milestones. Perhaps they'd celebrate First Breath Day, commemorating when the atmosphere became breathable in a particular region, or Flowing Water Day, marking when permanent rivers first appeared. These celebrations would be uniquely Martian, with no Earth equivalent, creating cultural divergence between the two worlds. Music composed for Martian acoustic conditions would sound different than Earth music, as sound travels differently in Mars's thinner atmosphere. Martian architecture would develop its own aesthetic, shaped by the need to withstand dust storms, utilize local materials, and adapt to lower gravity. Martian cuisine would incorporate foods grown in Martian soil under Martian conditions, creating flavors that never existed before. A whole new branch of human culture would emerge, sharing roots with Earth but growing in its own direction. This cultural flowering would be one of the less tangible but perhaps most meaningful benefits of terraforming. It would represent human creativity and adaptability, our ability to not just survive in new environments but to thrive and create beauty. It would add new dimensions to human experience, new perspectives from which to view existence. Now I want to address something we haven't fully explored: the role of corporate interests in Mars colonization and terraforming. Companies like SpaceX are driving much of the current excitement and progress toward Mars. Elon Musk has been remarkably clear that his ultimate goal is to make humanity a multi-planetary species, with Mars as the first step. But SpaceX is a private company, ultimately beholden to its owner and investors. What happens when corporate interests and the long-term project of terraforming intersect? There's a risk that early Mars colonization becomes dominated by corporate entities that prioritize profit over responsible stewardship. Imagine a scenario where multiple corporations establish competing colonies on Mars, each exploiting resources as quickly as possible, with minimal coordination or long-term planning. The early days of Mars colonization could resemble the Wild West or the colonial exploitation of Earth's resources, with environmental damage and social inequity built into the foundation of Martian civilization. On the other hand, corporations might be more efficient at establishing initial infrastructure than governments, which are subject to political whims and budget fluctuations. The historical record shows both examples of corporations enabling massive projects and examples of corporate exploitation. Likely, Mars colonization would involve a mix of government agencies, private corporations, international consortiums, and eventually independent Martian entities, all with different priorities and methods. Regulating this complex mix of actors would be incredibly challenging. Existing space law, primarily the Outer Space Treaty, is vague on many relevant issues. It prohibits nations from claiming sovereignty over celestial bodies but doesn't clearly address corporate claims or the rights of settlers. As we approach actual Mars colonization, we need new legal frameworks, but achieving international agreement on such frameworks has proven nearly impossible. Different nations have different visions for space development, and those visions sometimes conflict. China, for instance, has its own ambitious space program and might pursue Mars colonization independently of Western efforts. Russia, India, and the European Space Agency also have interests in Mars. If we end up with multiple, poorly coordinated attempts to terraform Mars, the results could be chaotic. Different factions might pursue conflicting terraforming strategies, or might sabotage each other's efforts out of competition or ideological differences. The dream of terraforming could become a nightmare of conflict and wasted resources. This is why many space advocates argue for robust international cooperation before we seriously attempt terraforming. They suggest we need something like an international Mars Authority, with representation from all major spacefaring nations and the power to coordinate terraforming efforts, allocate resources, and resolve disputes. Creating such an authority would require unprecedented global cooperation, but without it, the alternative might be chaos or conflict. Let me share some recent discoveries that have changed our understanding of what's possible on Mars. In 2020, scientists announced evidence of active methane releases on Mars detected by both the Curiosity rover and orbiting spacecraft. Methane is significant because on Earth it's primarily produced by biological activity, though it can also be generated by geological processes. The methane detections were sporadic and localized, suggesting some active process is releasing it. If the source is biological, it would mean Mars harbors life right now, even in its frozen state. This would have profound implications for terraforming. We'd need to understand this life before we alter the planet. If the source is geological, it suggests Mars is more geologically active than we thought, which could mean there's more internal heat available than our models predict. Either way, the methane mystery changes our understanding of Mars. Similarly, ground-penetrating radar data has revealed extensive subsurface ice deposits at various latitudes, not just at the poles. This ice could be a crucial resource for future colonists and terraforming efforts. The more accessible water ice we find, the more feasible it becomes to establish widespread settlements and provide the water needed for a transformed ecosystem. NASA's Perseverance rover, which landed in February 2021, is currently collecting samples that may eventually be returned to Earth for detailed analysis. These samples could contain evidence of ancient Martian life or provide detailed information about Martian geology and chemistry. Every piece of information we gather about Mars refines our understanding of what terraforming would entail. The James Webb Space Telescope, launched in December 2021, while primarily focused on distant galaxies and exoplanets, has capabilities that could be used to study Mars's atmosphere in unprecedented detail. Future observations might reveal trace gases or atmospheric dynamics we haven't detected before. Our picture of Mars is constantly being refined, and each new discovery could support or challenge our assumptions about terraforming. Here's something that should make you wonder. What if we're not the first to terraform Mars? What if ancient Martians, if they existed, attempted their own terraforming or climate engineering? This is pure speculation, but we know Mars had a thicker atmosphere and liquid water billions of years ago. What if an ancient Martian civilization tried to preserve their dying atmosphere and failed? Could we detect evidence of such attempts? Might there be ancient Martian technologies buried beneath the regolith, waiting to be discovered? Before you dismiss this as science fiction, consider that we're only beginning to explore Mars in detail. We've examined tiny fractions of the surface with rovers and studied it from orbit, but we haven't conducted thorough archaeological surveys or deep drilling. If a civilization existed on Mars billions of years ago, nearly all evidence could have been erased by geological processes, radiation, and time. But perhaps not all evidence. Some anomalies photographed by Mars orbiters, like unusual geometric patterns or symmetric formations, have sparked speculation about artificial structures, though conventional explanations are far more likely. The point isn't that ancient Martians definitely existed, but that we should remain open to surprising discoveries as we explore Mars more thoroughly. And if we did find evidence of a previous civilization, even a simple microbial one that briefly flourished billions of years ago, it would completely reframe our approach to terraforming. We'd be not creating something new but restoring something lost, which carries different ethical weight. As we approach the conclusion of our journey through the terraforming of Mars, let's return to the present moment and consider what you can do. You might think that planetary engineering is so far beyond individual action that there's no point in engaging with it. But the decisions made in the next few decades about space exploration, Mars colonization, and eventually terraforming will shape humanity's future for millennia. Public support for space exploration influences government funding and policy. Your taxes, in many countries, partially fund space agencies. Voting for leaders who prioritize space exploration, or who emphasize international cooperation versus nationalistic competition, affects the trajectory of space development. Supporting educational programs in science and engineering ensures future generations have the skills needed for these grand projects. Even simply staying informed and discussing these topics helps build the cultural foundation necessary for multi-generational projects. Ask yourself, do you want humanity to remain earthbound, or do you support expansion into the solar system? If you support expansion, what values do you think should guide it? Should Mars be preserved as wilderness or transformed into a new home? Should Mars colonization prioritize scientific research, commercial development, or creating a backup for Earth's biosphere? Your answers to these questions, multiplied across millions of people, will influence the actual course of events. There's also the question of how terraforming Mars relates to fixing Earth's environmental problems. Some critics argue that fantasies about terraforming Mars distract from the urgent need to address climate change, biodiversity loss, and pollution on Earth. They say we should focus on preserving the one habitable planet we have rather than dreaming about creating another. This criticism has merit. We absolutely need to address Earth's environmental crisis. But the two goals aren't necessarily in conflict. Technologies developed for Mars colonization, like closed-loop life support systems, efficient resource recycling, and renewable energy, directly benefit Earth. The systems thinking required to terraform a planet could help us better manage Earth's complex ecosystems. And psychologically, having a bold, inspiring goal like terraforming Mars might actually motivate the kind of long-term thinking and global cooperation we need to solve Earth's problems. Imagine if addressing climate change was framed not just as preventing disaster, but as practice for planetary management skills we'll need to terraform Mars. Suddenly, it's not just about sacrifice and limitation, but about developing capabilities for an exciting future. This reframing might engage people who otherwise tune out environmental messages. It's a controversial approach, and it shouldn't minimize the urgency of Earth's situation, but it might be more motivationally effective for some audiences. The timeline for terraforming Mars, as we've discussed, spans centuries to millennia depending on the approach. But the decisions that determine whether it happens at all will be made in the next 50 to 100 years. This is the critical period when we either commit to becoming a multiplanetary species or we don't. The infrastructure, legal frameworks, international cooperation, and technological foundations needed for terraforming must be established now, even if the main work happens later. We stand at a unique moment in history. For the first time, we have the theoretical knowledge to terraform a planet. We're developing the technological capabilities, though we're not there yet. We have identified a suitable candidate planet within reach. And we have strong motivations, both the positive goal of expanding human civilization and the negative pressure of existential risks to earthbound humanity. Whether we actually pursue terraforming depends on choices being made right now by people alive today. Think about the weight of that responsibility. Decisions made in conference rooms, laboratories, and voting booths over the next few decades could determine whether humans ever walk under an open Martian sky, breathing freely on a world our ancestors transformed. Or they could determine that Mars remains forever untouched, a pristine wilderness that we chose to preserve rather than exploit. Either choice echoes across millennia. As we've explored together, terraforming Mars would be staggeringly difficult, requiring technologies we haven't fully developed, cooperation on scales we've never achieved, and commitment spanning more generations than we can imagine. It would be expensive, risky, controversial, and uncertain. But it would also be magnificent, the ultimate expression of human capability and ambition. It would make us a multiplanetary species, would advance our scientific understanding immeasurably, and would create opportunities for growth and development that we can barely imagine. The partially terraformed Mars we imagined earlier, with its mauve skies, seasonal streams, and hardy pioneer organisms, represents just one possible future among many. Perhaps we'll achieve full terraforming, creating a true second Earth. Perhaps we'll pursue para-terraforming, creating enclosed habitats while leaving the planet itself largely unchanged. Perhaps we'll decide that Mars should remain pristine, and we'll visit but not transform it. Or perhaps we'll never establish more than small research outposts, and the dream of terraforming will remain forever just a dream. What's certain is that Mars will be part of humanity's future, one way or another. It's too close, too similar to Earth, and too full of potential for us to ignore. Even if we don't terraform it, we'll study it, visit it, learn from it. Every Mars rover and orbiter is adding to our knowledge. Every advancement in rocket technology makes Mars more accessible. Every year brings us closer to the point where humans will walk on Mars's surface, and then we'll have decisions to make about what comes next. I want you to imagine something one more time. Picture yourself centuries in the future, on a Mars transformed beyond recognition from the frozen desert it is today. You're standing on the shore of a Martian ocean, watching waves lap against rust-red sand. The sky above is blue, streaked with clouds that look almost but not quite like Earth clouds. Behind you, forests climb the slopes of ancient volcanoes. The air you're breathing, the water in that ocean, the life spreading across this world, all of it exists because your distant ancestors decided to make it so. Or imagine the opposite. You're standing in the same location, but Mars remains as it is now. The thin atmosphere barely whispers around you inside your protective suit. The landscape is pristine, untouched, exactly as it's been for 4 billion years. There's a stark beauty to this wilderness, and you're glad it was preserved. Both futures are possible. Both have value. The question is which future you want to create. The story of terraforming Mars is ultimately a story about humanity itself. It's about who we are, what we value, and what we're capable of achieving when we work together toward a common goal. It's about the tension between preservation and transformation, between caution and boldness, between accepting the universe as it is and reshaping it to suit our needs. It's about the longest of long-term thinking, about making decisions whose full consequences won't be known for thousands of years. As you've heard this exploration of what it would take to terraform Mars, what challenges we'd face, what benefits we might gain, and what questions remain unanswered, I hope you felt some of the wonder and complexity of this grand vision. Whether you conclude that terraforming Mars is humanity's destiny or hubris, something to pursue or avoid, your engagement with these questions matters. We are, right now, the generation that stands at the threshold. Behind us, all of human history on Earth. Before us, the possibility of a future among the stars, beginning with Mars. The rust-colored world that's hung in our sky since before we had words for it might one day turn green and blue, might one day ring with human voices and the sounds of life where there's been silence for eons. Or it might not. The story is still being written, and in some small way, you're one of the authors. The choice facing humanity isn't just whether to terraform Mars, but what kind of species we want to be. Do we play it safe, huddling on our home world? Or do we reach outward, accepting risk in exchange for growth? Do we preserve pristine wilderness even on other planets? Or do we transform worlds to suit our needs? There are valid arguments on all sides, and the tension between these positions is healthy. It forces us to think deeply about our values and our future. What's undeniable is that the technical capability to at least begin terraforming Mars is within our reach, if not now then within the next century or two. Whether we develop the political will, the international cooperation, and the long-term commitment necessary is the real question. Mars isn't going anywhere. It will still be there, frozen and waiting, whether we take 10 years or 10,000 years to make our next moves. The universe is patient. The question is whether humanity is bold enough to try transforming a world, wise enough to do it responsibly if we try, and thoughtful enough to preserve what should be preserved. The dream of a green Mars, of rivers flowing through Valles Marineris, of forests climbing the slopes of Olympus Mons, of human children born under Martian skies who will never see Earth except as a bright blue star, that dream has captured imaginations for over a century. Scientists and engineers are turning that dream into blueprints and calculations. Someday, perhaps sooner than we expect, those blueprints might become reality. And you'll be able to say you were alive when humanity first seriously grappled with these questions, when we transitioned from dreamers to planners to doers. The red planet waits, silent and cold, beneath a butterscotch sky. It's been waiting for 4.5 billion years. We can wait a little longer while we figure out who we are and what we want to become. But one day, if we choose to, we might answer Mars's silence with the sounds of life, might warm its frozen deserts, might fill its empty sky with birds that have never existed before. We might make Mars not just a second Earth, but something new, a unique fusion of human vision and Martian reality. That future, if it comes, will be built on choices made today, on missions launched, technologies developed, questions asked and answered, on international treaties signed or unsigned, on the education of children who will become the scientists and engineers of tomorrow, on your choices, in whatever small ways you influence the trajectory of human civilization. The story of terraforming Mars is beginning now, even though the main events lie centuries ahead. And you're part of that story, whether you intended to be or not. So as you go forward from here, carry these questions with you. What kind of future do you want for humanity? What are you willing to sacrifice or invest to achieve that future? What should be preserved and what should be transformed? How do we balance caution with boldness, wisdom with ambition? The answers aren't simple, and they're not the same for everyone. But wrestling with these questions makes us better, more thoughtful, more prepared for the challenges ahead. Mars gleams in the night sky, a red eye watching, waiting, challenging us to be more than we are. Whether we answer that challenge by preserving Mars as it is or by transforming it into something new, the attempt will define us. The greatest adventure in human history might be just beginning, or it might remain forever a beautiful dream. Either way, the story of humanity and Mars is far from over. In fact, it's really just beginning. And what happens next is up to all of us.